Good afternoon. This is Pete Burns with the Energy Conservatory. I want to welcome you all today to our webinar on zonal pressure diagnostics, featuring our speaker Rick Karg. Zonal diagnostics has been around since the early 90s for a lot of weatherization and insulation contractors. This was a technique that really kind of came to the forefront based on an article that came out in Home Energy magazine, article written by Jim Fitzgerald, a Minneapolis-based insulation contractor, and dense-packed cellulose guru, Energy Conservatory's own Rob Nevitt, and Michael Blasnick, at the time working for, I believe it was Procter Engineering. The article called "User-Friendly Pressure Diagnostic" really kind of changed things for insulation contractors and weatherization guys, in that it allowed us or gave us a tool to actually measure air leakage, measure and quantify air leakage pathways in the building envelope. As I said in the past, we were just using blower doors to test pre and post, but this tool, this gave us a tool to actually measure air leakage in various zones to ensure safety first and foremost. We wanted to make sure that we weren't leaking air from attached garages into the living space, or from crawl spaces into our living space, crawl spaces that could have mold or moisture issues into our living space. For durability issues up here in up in Minnesota, in bitter cold climates, we've got moisture-laden air. If it's moving up bypasses or pathways up into those attics, we'd see it. It'd be a durability issue on our buildings. And finally, for energy savings, if again those same air leakage pathways can create an energy penalty on the building. That said, let's turn it over to Rick Karg. Rick was trained as an economist, worked as a building contractor. He's been the president of R.J. Karg Associates for about 30 years now. He's worked with many low-income weatherization programs, home performance programs, electric and gas utilities, and Rick is also a member of the ASHRAE 62.2 Ventilation Committee. Rick, let's turn it over to you.
Thank you, Pete. As Pete said, we're going to talk about zone pressure diagnostics. This is a very useful tool for weatherization and for new construction, but primarily for existing construction. We are going to talk about, first of all, a bit of an introduction, which Pete gave you a bit of history about that, which is very useful. And we've come up for this presentation with some new terms that I hope aren't confusing. The point is to make them as clear as possible. However, they are a bit stuffy, and I'll say more about that as I go on. Something I want to talk about a bit is how zone pressure diagnostics is used in an incorrect way in some programs, and we'll get to that as we move along. So we'll look at non-modifiable zone analysis and modifiable zone analysis. And as we move through this, we will be using the Residential Energy Dynamics tool, or ZPD tool, as I go through it. At the end of the presentation, I hope to have one of those in front of us live so I can show you what it does. I should tell you, I don't recall Pete saying this, but I am the president of Residential Energy Dynamics and was very much involved with this particular tool. So first of all, introduction. These are the tools that are required. You must have a blower door to do zone pressure diagnostics. By the way, it's sometimes called series leakage testing. You've got to have a blower door. You need 1 or 2 manometers. Digital manometers are by far better than the older analog ones. And I recommend that you have 2 digital manometers. It makes it much easier. I know that's more costly, but if you can get your hands on an extra one, Doesn't have to be a brand new one. It can be an older, for example, DG2 or DG3. It makes it much easier to do the testing. For modifiable zone pressure testing, you need a calculation tool. It's very difficult to do it without a calculation tool. And as I said, we are going to be using the Residential Energy Dynamics tool. And from here on, I will probably call that RED as an acronym, the RED Zone Pressure Diagnostics tool. It's important to understand that in our homes, we have pressure boundaries. You might call them air barriers. I'm going to call them pressure boundaries during this presentation. And you see in this diagram, we got an attic that's an unconditioned attic. Nobody's living up there, a few suitcases and some other old stuff up there. The roof acts as a pressure boundary. This is a very important thing to understand. And of course, the ceiling or the attic floor acts as a pressure boundary. That's very important. And so the pressure boundary here. And it's important that you understand that the roof acting as a pressure boundary is important because very often we add attic ventilation to a house. We put in attic venting, and that destroys some of the pressure boundary characteristics of the roof. Well, on the one hand, that's the point of attic venting, but on the other hand, it can in some cases increase the whole house CFM 50 if we add attic venting, and I'll say more about that later. Of course, the wall is a pressure boundary, and here we have the basement ceiling can be a pressure boundary, even though the basement is, in this case and in many cases, what we would call within the thermal and pressure boundaries of the structure. We can still treat the basement as a zone and do zone pressure testing to the basement. This table shows the various zones that we can have in houses, the most common ones: attic, crawl space, basement, garage, and knee walls. And in the second column shows the interior pressure boundaries of those zones, and in the final column the exterior pressure boundaries for those zones. So there is a great deal that we can do to test. We can do pre and post to see how we've done with air sealing. As Pete mentioned, we can also make sure that bad air from a crawl space is not coming up into the house. The objectives of zone pressure diagnostics, Pete mentioned a number of these. We can determine the leakage, the flow rate, the actual flow rate from an area from the house, like the attic to the house, or the basement to the house, the crawl space to the house. We can determine the leakage from the zone to the outdoors. This can be helpful, for example, from the attic to the outdoors. And you will see how we can determine the effective attic venting square inches when we do the testing. We then can also determine the through zone or total path CFM 50 flow from the house to the outdoors through the zone. And I will explain that as we go along through a couple of examples. We can appraise indoor air quality issues, such as, well, what's the connection of an attached garage to the house? We want that connection to be very poor. We want the common wall between the house and the garage to be very tight. Zone pressure diagnostics can help us with that. Of course, we don't want carbon monoxide getting into the house. More objectives. We can determine the effectiveness of air sealing pre and post. Some low-income weatherization programs are doing this. For example, the state of Wisconsin and the state of Maine are two that I know of, and I'm sure there are others. How effective is the air sealing? Well, we can find out by doing zone pressure diagnostics before and after. And the states I just mentioned, Wisconsin and the state of Maine, and I'm sure others, are using air sealing targets, and because zone pressure diagnostics allows us to establish a metric or put a number on our leakage, we can establish a target expressed as CFM 50. And as I've already hinted at, zone pressure diagnostics demonstrates the downside of adding attic venting, because this can increase energy use for the house. So just as a general rule, ventilate an attic as you need to, but do not ever over-ventilate an attic. This again, in this diagram, this illustration shows the zone being the attic, and the zone, this is a pressure boundary, and the roof is a pressure boundary, and the attic floor is a pressure boundary. For zone pressure diagnostics, we get the house as close to 50 pascals as possible, as we do in a normal blower door test. And that can be negative 50 pascals or positive 50 pascals. It doesn't make any difference. You can do it either way. A guideline for zone pressure diagnostics is that each pressure boundary, I hope by now you know what I mean by a pressure boundary if you didn't before, let's say the roof and the attic floor, each pressure boundary imposes resistance to airflow. And the higher the pressure difference across that boundary, the greater its resistance to airflow. Now the next diagram, illustration, will show that. Here we have a house, and we've got, with the blower door operating at 50 pascals, this would be negative 50 pascals because we're blowing air out of the house with the blower door fan. With our manometer, if we measure the pressure difference from the house, where this fellow is standing, to the attic, this tells us it's 37 pascals. And if we then measure the pressure difference from the attic to the outdoors, and this is actually very simple to do, I'll show you how, that is 13. Notice, if you will please, that these two numbers, the 13 and the 37, add up to 50 pascals. As we would expect, we're depressurizing the house to a level of 50 pascals, so 37 plus 13 gives us 50 pascals. In our testing, we should always have these two numbers, if we're using the attic as a zone, add up to 50 plus or minus 2 pascals. This is the RED zone pressure diagnostics tool. I'll mention in just a moment how this was created. It's a little difficult to see here. I imagine it's quite small for you. You can go take a look at it. Here's the website address, www.residentialenergydynamics.com. There are about 25 calculation tools there now. This is just one of them. Just quickly to orient you, we've got the, you can up here on this line, you can put the name of the job, the blower door test type. You must select pressurization or depressurization. That must be correct for the test that you're doing. Now notice that the tool is in sections. This section used advanced inputs. I will mention that later on. This is an important section, the initial zone configuration. This is the way you arrive at the house. This is before any hole is created by opening an attic hatch or by opening a basement door or a door to the garage. So that's what initial zone configuration means. And then we have the next section of the tool is modified zone configuration. This is the data for the zone in the modified condition. For example, an attached garage, and now you've opened the door from the garage to the house or from the garage to the outdoors. Finally, at the bottom section of the tool is the results for the initial zone. Now, the results are for the house in the initial zone configuration, not in the modified. We modify the zone in order to arrive at the results. That's the only reason we modify it. But these results are based on the initial zone configuration. For example, if we're testing if the garage is a zone, these results at the bottom are for the garage with the doors closed. And we will look at the tool a bit more closely as we go along and do some examples with a live tool. The credits, and one of the reasons I am delighted to be doing this session with the Energy Conservatory is because Colin Olson of the Energy Conservatory helped us with this tool. And the Energy Conservatory has a free ZPD utility at its website. If you go there and go to software, you can find it. As far as I remember, it only works on PCs. It does not work on Apple computers. But our method with the RED tool is based on the method that the Energy Conservatory put together. It's a bit different, but it's very much based on it, and we were very happy to have Colin Olson's help for the development of our tool. Anthony Cox also helped. Many of you, I think, have received training by Anthony and know him. Wonderful fellow and an excellent trainer. The guys at RED, that's me and my business partner Charlie Holly. And as I've already said, our tool is based very much on the Energy Conservatory ZPD utility tool. Again, that's free on the Energy Conservatory website. So, first of all, I want to go into the non-modifiable zone analysis. Again, this is a very stuffy term, but I think it describes what we are talking about. You are unable to modify the zone. You cannot, because of the geometry of the zone, make any significant changes such as open a hatch or open a door. For example, a ceiling that is attached to a porch with a ceiling that's attached to a house. And we might want to know if that ceiling area is attached to the second floor cavity. That would be a non-modifiable zone analysis. And we'll look at that with some illustrations in front of us. This allows the analyst to determine if the space is connected by airflow, but we cannot determine the flow rate. The flow rate is CFM 50, and the pressure is in terms of pascals difference. So we must have the blower door running, and then with our digital manometer and some hoses, we check to see what the pressures are. We'll look at some cases like that. We have to be very cautious with this technique because it can lead to false conclusions. And as something I've already mentioned is that the house to zone delta P, or difference in pressure, plus the zone to outdoor difference in pressure is equal to the house to outdoor pressure difference. In other words, going back to the example I've already shown you, if with the blower door we are creating a house to zone delta P of 50 pascals, then this pressure difference and this pressure difference will add up to 50 pascals. Examples of non-modifiable zones are joist cavities in Cape Cod style houses. In some parts of the country, Cape Cod is called story and a half. In New England, where I live, they're usually called Cape Cod style houses. Crawl space with no access. There's no way to get down there, but it's there. It's a space, it's a zone, but you can't get there. Soffit area above kitchen cabinets. This is a classic example of leakage in many homes. An attached porch roof ceiling cavity, and I'll show you an illustration of that. Now, this is a basic principle of zone pressure diagnostics, and it has to do with non-modifiable zones. This is a rather silly illustration, but I hope it makes the point. We have a house, and I have drilled 4 holes in the roof and 2 holes in the attic floor. All of those holes are of the same size. Let's say they are 1 foot in diameter. 4 holes in the roof, 2 holes in the ceiling. Now, let's assume there are no other leaks in the roof, no other leaks in the ceiling, and of course there are gable ends. We'll assume those are perfectly tight. You can see just by this that the roof has twice the leakage rate as this pressure barrier with these 2 holes. So with 4 holes in the roof, we have twice the leakage as we have here with 2 holes in the attic floor. That would result in, if we have 50 pascals of pressure created by the blower door, that would result in a pressure difference between the attic and the outdoors of 13, and a pressure difference between the attic and the house of 37 pascals. And that tells us that the roof has twice the leakage as the attic floor. Now, keep that in mind when we go to the next illustration. Notice again, we've still got 4 holes in the roof and we've got 2 holes in the attic floor, but the size of the holes is much, much bigger now than before. But notice that the pressure differences between the zone and the outdoors are the same. We have 13 and we have 37, just as we had before. In other words, with the pressures alone, you cannot determine how significant the leakage is. You can only determine the relationship between the leakage in one pressure boundary and the other. In this case, the roof gable ends and the attic floor. So we must be careful about that. This is pressures and relative leakage. This gray highlighted row, I highlighted it because it corresponds with the previous 2 illustrations. If the house to zone is 37 and the zone to the outdoors is 13, that means we have this leakage relationship. In other words, the zone to the outdoors has twice the amount of leakage as the house to the zone. Of course, if we have house to outside pressure difference the house to zone pressure difference of 25 and the zone to the outdoors pressure difference of 25, we can conclude then that the leakage area in each pressure boundary is the same. We have a 1-to-1 relationship. This information is given to you in the RED tool. It's one of the results that are reported. This is a case of a non-modifiable zone, this porch roof. In a house like this, it's got 2 floors, and it might be a Victorian house, balloon framing, and I hope you know what that is. In a case like this, if there is a ceiling on this porch roof, it could be that the 2nd floor cavity of this house is connected to the enclosed porch roof ceiling structure. We don't want that to happen. And we can determine if it's connected by using a non-modifiable analysis. That is, we run the blower door, depressurize the house to 50 pascals. We put a hose from a manometer up into this roof ceiling structure of this porch, and you might, my question, I'm not going to be able to hear your answers, maybe if you shout loudly. My question is, if we got a pressure of 20 pascals from this porch roof to the outdoors, would that porch roof be connected to the second floor cavity? And the answer is yes, it would be. What we would want if there were no connection, if we did a pressure measurement from the ceiling roof structure of this porch to the outdoors, what we would want is 0, which would mean no detectable connection. So non-modifiable zone analysis can be useful, but we must be careful with it. In this particular case, this is this porch roof ceiling structure is non-modifiable. We cannot create a temporary hole without being destructive. Now, misuses of non-modifiable zone analysis are fairly common out there. It's a state in the low-income weatherization program that was using non-modifiable zone analysis as a target. They said that if the house-to-attic pressure difference was 45 or more, that it was fine and no air sealing in the attic had to be done. Now, some of you know what that means. Let me show you with this illustration what we've got. Now, the roof in this case is 4 times leakier than the ceiling. Let's say for this weatherization program that I'm referring to, I'm not going to tell you which state this was, and perhaps other states were doing this also. Their target was, we want for this value, when you depressurize the house to 50 pascals and measure with your manometer from the house to up to the zone, that this pressure needed to be 45 or higher. Now, I could, as a weatherization person, if I was onto this, I could come to this house and add attic ventilation. If I add attic ventilation, what does that do to the pressure up here? Right now it's 8. If I add the attic ventilation, I am lowering the resistance to airflow of this roof gable end pressure boundary. That lowers this number. So what if I take this 8 down to a 4 by adding attic ventilation? What then automatically happens to this 42? If this one is 4, this becomes 46, and now I am in compliance with this weatherization program's target, and I have done nothing to air seal this very important pressure boundary. So you can see how just using a non-modifiable or just pressure target can go wrong. It's not a good thing to do. If we have targets, they should always be based on flow, and I'm going to get to that next. Modifiable zone analysis allows us to calculate the flow. Now, when you're doing a blower door test, you depressurize or pressurize the house to 50 pascals. So that is the pressure difference, and what you are finding is the flow expressed in units of CFM 50. For zone pressure diagnostics, it's the same thing. We have the pressure differences, and we calculate the flow in terms of CFM 50. And we'll do some examples with this. So as I just said, it allows the analyst to determine the flow through 2 pressure boundaries in series, both individually and together. So we have to operate the blower door while we're doing this test. We need to be able to modify the zone. If we cannot modify the zone, then it's a non-modifiable zone analysis, and we can only look at pressure differences. But if we can create a hole, if we can open a door, that is, or open an attic hatch. And with the ZPD tool from RED, you can also close an existing hatch or attic door, and we'll still give you results. If we're able to do that, to modify the zone temporarily without causing destruction, we don't want to use a Sawzall for this. We want to open something and be able to close it. We can determine the CFM50 flow, house to zone, zone to outdoors, and through zone, which is often called total path. And this is really great. Once we have the CFM50, we can divide those numbers, some of them anyway, by 10, and that approximately, and that gives us the square inches of leakage through the pressure boundaries. That's extremely powerful. And this is a really good test to be able to do for quality assurance. For example, how well did the crew do at sealing the attic floor? How well did the crew do at sealing the common wall between the house and the attached garage? Zone pressure diagnostics allows us to determine that. So in the modifiable zone analysis, we add a hole or we open a door. And as I said, with the RED ZPD tool, we can close a door or close a hole up. The only time I've ever done closing instead of opening is when I've done it to an attic, and my only option was to close attic vents. And that might come up sometime. It's come up for me, and the RED tool will do that for you. Now, those of you that have done zone pressure diagnostics previously will find the RED tool easier, I think, because you don't need to distinguish between opening an attic hatch, or what we used to call adding a hole or opening a hole, or opening a door. They're all incorporated into one. There's no measurement of the opening required. So all is the same tool is used for all analysis. This is, I imagine, what some of you have used in the past. This is the method that, based on the advanced zone pressure diagnostics study that was done in about 2001. Wisconsin was involved with this, field testing this. The Energy Conservatory was involved. Many of the people that Pete mentioned in his introduction were involved in this study. And based on that, this was a method that was devised for adding hole, and this was the work of Anthony Cox and Colin Olson. Of course, you can still use this, but it's an older method, and I think the RED tool is easier to use than this. However, this is very colorful. I've always liked the colors of this chart, and it's a good method to use. This, likewise, Anthony Cox and Colin Olson devised this chart, and this is for opening a door, either from the garage to the house or from the garage to the outdoors. This is a fine method to use if you wish to use it, and I do not mean to indicate that this or this one should stop being used. If they are suiting your needs, that's just fine. There's nothing at all wrong with these methods. Examples of modifiable zones include the old standby attics, attached to garages. We can use basements. Now, attics, by the way, are almost always unconditioned. They're cold in the wintertime and very hot in the summertime. Basements, on the other hand, many basements are considered conditions. That doesn't mean you can't use a basement as a zone or an attic as a zone. For example, you can determine the square inches of leakage from the basement to the outdoors by using zone pressure diagnostics. And you can do that pre and post weatherization. That's an important thing to know. Crawl spaces can be used as a zone, but only in this case because we're talking about modifiable zones. They would have to be a crawl space that has that you can create an opening into.
Rick? Rick?
Yes.
Hello? Yeah, hey, got a question from someone online here. Question is, when opening a hole in the attic, if I use the attic hatch as the hole, do I open the hatch fully Or do I just crack the hatch enough to get the hose into the attic? Also, if I just crack the hatch, would I seal around the hose with tape or something?
Two good questions. I hope everyone heard that. First of all, with the most current tools for zone pressure diagnostics, for where you have a modifiable zone analysis, you can just remove the attic hatch entirely. So in the early days of zone pressure diagnostics, we used to hold the attic hatch open. We didn't want to open it too much in some cases, and we needed to measure the square inches of opening. With the RED tool, that's not necessary to measure the square inches of opening. So what you can do is do your initial testing, your initial configuration with the attic hatch closed. You put a hose up in the attic and close the hatch on the hose. There's no need to seal around the hose, but it is important to make sure that the hose is not totally crimped by the attic hatch. And I have found in my experience that the manometer will indicate if the hose is totally crimped, because you'll have usually a fairly high pressure value that holds fairly steadily on your manometer. If it's not crimped, you'll have variation in your pressure values on your manometer, and they'll be fairly low, hovering around 0, of course, until you start the blower door. Then they'll be around 50. But no need to seal around the hose, and with the RED ZPD tool, you can just move the attic hatch piece of wood or whatever it is, you can get it out of the way. It's a good idea when you put the hose up in the attic to have it about the end of the hose about 3 feet away from the attic hatch, and make sure that nothing is restricting the end of the hose. Two good questions. Now, I'm showing a picture of the Energy Conservatory DG700. Many of you are familiar with this piece of equipment. I found when I was learning zone pressure diagnostics that the most difficult part for me was figuring out how to connect the hoses to the manometer. I'm going to assume for a moment here, while I talk about this for a bit, that we have a separate manometer at the blower door, so that we know that the house is at 50 pascals of pressure. And we also need, for the RED tool, we need to know what the whole house CFM50 is. Notice that this manometer, if you can see it, is set to, the mode is set to PRPR, that's pressure, so we can measure pressure on both sides. I think that as you get into zone pressure diagnostics and using the manometer, it's very important to develop your own method of understanding what's going on. What works for me is to assume that there's a WRT with reference to. That's what that means right here at this position. Here's one tap, the top tap, called the input tap, and here's the reference tap. If I want to measure the pressure from the attic to the house, I would put a tube on this top tap. I would throw that tube or that hose up in the attic, and then I would be standing down below in the house, and this tube would have no hose on it. So it's taking the pressure of the house, and the one up here is picking up the pressure of the attic through the hose. So I would have the attic with reference to the house. That's how I remember it. This took time for me if you're just starting with zone pressure diagnostics. Give yourself a break, let it take time, think about it, ponder it, and it will come to you. Ask others about it, they might have some helpful suggestions. But the with reference to works very well for me. And figuring out and instructions on how to hook up the manometer in every situation is a bit beyond this webinar, but it is something that's very important and you should work on that. It's much better to be able to do that in a hands-on fashion. So here we have a little bit more about manometer use. I've got the blower door running, depressurizing the house to 50 pascals, and here is the digital manometer, DG700. I am measuring now on the right side of the manometer. You can see 32 there, I think. I'm measuring the house. The top tap is open, so it is measuring the pressure in the house, and the bottom tap has a hose on it that's going into the attic. So I have the house with reference to the zone, and the house with reference to the zone is negative 32 pascals. And then on the left side of the manometer, I have the house with reference to the outdoors, and that's giving me a reading of 50 pascals. So that's the, yes.
I've got a question.
Yes.
Location in the house with respect to the house, or should it be located far away from the hatch or opening?
It's another good question. It's a good idea to make sure that air is not passing over the open-ended taps. So because that air can have an impact on your readings on your manometer. Likewise for the end of your hose. Make sure that flowing air is as best as you can, that flowing air is not going over the end of your hose or the end of your open tap. Otherwise, you should be fine. For example, in the attic, the pressure in the attic is going to be somewhere near the center of the attic. It's going to be pretty consistent all around that center of the attic. It could be if you get it right to the edge of the attic, you're going to get airflow from the outside, and that will affect your reading. So try to stay away from any airflow that's coming into the attic, for example. Now next, what do we do to measure? It seems perhaps a bit mysterious. How do we measure the zone to the outdoors without going up in the attic, without climbing on the roof? All we do, I'm going to go back to the previous slide. You can see that the blue hose is now connected on the right side and the bottom. I'm going to move that blue hose so it's connected left side to the top. So now we have it's up in the attic, we have the attic with reference to the outdoors. The green hose is outdoors, attic with reference to outdoors, and that gives us 18. And the negative 18 and the negative 32 add up to 50 pascals as they should. So that's a little bit about hooking up the manometer. Again, it's a good idea if you have two manometers, one at the blower door and leave it there, and one to carry around with you and measure zones. You can do it with one manometer. You just have to take the manometer away from the blower door, carry it around with you, and you can always have a green hose going to the outside and periodically check to make sure the house is still at 50 pascals. By the way, whenever you open a hole, it only makes sense that the pressure in the house will go down. So you have to increase the RPM of the blower to keep the house pressure at 50 pascals. So an example of using modifiable zone analysis to the attic using the RED tool. So what we are going to do is we're going to open the attic hatch in this case, and that is our modification. And we'll use the RED tool. We will create, usually as a general rule, this is a good one to follow, try to create a hole in the tighter of the two pressure boundaries. For an attic, that is almost always, I hope, going to be the attic floor rather than the roof itself. If the roof is the tighter pressure boundary, you better do some weatherization before you do zone pressure diagnostics. And then when you do create the temporary hole, it's important to create a significant pressure shift. And I will explain that, but the RED tool gives you uncertainty values, and if you play with it some, play with your testing, it will teach you how to get more and more accurate with your testing because of its reporting characteristics. And try to create a significant modified CFM50. That will become more clear in just a minute. So here's our test house. This is an attic example. So in the initial condition, initial zone configuration, stated up here, we've got the attic to the outdoors is 18 pascals, and the attic to the house is 32 pascals. The attic hatch is closed. I hope that's clear. I'm sorry the diagram's off a bit. The hose to the attic should be going through the attic hatch, and then the hatch should be closed on the hose. But you can see here we have, on the digital manometer, we have negative 32 pascals house to zone, or house to attic. And we have 50 pascals from the house to the outdoors. Something that you need to do with the RED ZPD tool, and it's in the blue or purple box here, we need to measure the whole house CFM50 with the temporary hole closed. And I'm assuming it's 2400, part of the example. Now we modify a zone. Look at the RED tool in just a moment and you see how these numbers play out. We modify the zone. Modification means that we open a hole, we open a door, and we then do the test again. Now in this case we are opening the attic hatch. It would be perfectly fine just to take the attic hatch off altogether and put it aside. Bring it down and set it in the floor, or put it on the floor in the attic. Just get it out of the way. That's important to keep in mind. And the blue hose should still go up. Yes?
We had a question. Are you, in this configuration, are you cruising at minus 50 when you're manipulating the hatch like that?
Really good question. Thank you for that, whomever brought that up. If you set your digital manometer that's at the blower door, the one that's at the blower door, in this case controlling the blower door, you can put it on cruise control, and as you open this hatch and take it off, it will automatically increase the revolutions of the blower door and keep the house at 50. So if you use the cruise control on the DG700, and as far as I know, that's the primary reason that the Energy Conservatory put cruise control on the DG700, to automatically keep the blower door at 50 as you opened and closed holes for zone pressure diagnostics. So yes, and if you don't have cruise control on your digital manometer, or you don't want to use it, you would have to do this manually. So when we open up this hole, we are not only destroying some of the integrity of the attic floor pressure boundary, but we are also making the whole house looser, so our whole house CFM50 will go up, and the pressure, the house pressure, will go down. So we have to increase the revolution RPM of the blower door fan with the variable speed control to make sure the house stays right around 50 pascals. By the way, with the RED tool, you don't have to get right back up to 50. In some houses, when you create the hole, you can't get back to 50. The RED tool can deal with that. So when we open the hole, now as we would expect, the whole house CFM50 goes up because we've just created a fairly significant hole. The RED tool needs that as an input also.
Rick?
So here's the, yes?
On the prior slide, you go back one slide, people are asking about PA2.
Okay. Let me go back to the just some simple notation that's helpful that you asked that. PA1, the pressure 1 is with no hole, generally, in notation for some people like me that do testing like this. So PA1 means the initial zone, and going to the next slide with the hatch open, the modified zone is PA2. So the pressure from the attic to the house, or house to attic, goes from negative 32, and then we open the hatch up, to negative 15. So 2 signifies the modified zone, 1 signifies the initial zone. Now here's the RED tool. Again, I want to point out, here we have initial zone. This is where the input for the initial zone goes. This is where the input to the modified zone goes when we open a hole. So, blower door off is where we would put a baseline. I haven't said anything about baseline yet, but if you're using auto baseline on your digital manometer, you would then put 0 in here as there's a 0 now. Blower door on, this is house with reference to outdoors, negative 50. So here it is subtracted. If you can see this, I hope you can. And soon it'll show up bigger on your screen, I think. And then we choose here, do we want to measure from the house to the zone or zone to the outdoors? We have a drop-down menu here. This is not a working copy on my slides, so I can't show it to you. But again, BD off, blower door off, is your baseline from the house to the zone or from the zone to the outdoors. I'm saying again that I'm assuming that baseline's either 0 or we're using the automatic baseline feature of the DG700, negative 32, which matches the example. Let me go back there. Negative 32, right there. That's where that comes from. And then the blower door flow adjusted to 50 pascals, 2400. Now, if for some reason you cannot reach 50 pascals, you use the corrected number that gives you what the leakage would be at 50 pascals. So that's where that 2400 comes from. And again, I will go back and show you that number on the example. In the initial zone, here it is right here, the 2400. That's an assumption that I made. If you notice this line on the blue tools, anything that is blue font, on the red tools, on the red tools, anything that's blue font is a result, anything that's black font is an input. So zone leakage ratio, zone to the house over zone to outdoors is 1 to 1.5. We talked about that in a table a while ago. So then the modified configuration. So now we have some choices up here. The hole is going to be created from between the zone and the house or the zone and the outdoors. Again, this is drop-down menu isn't working, but we have to choose where we're going to put the hole. And as I said, a good general rule is put the hole in the tighter of the 2 pressure boundaries, the one with the greater pressure across it. The type of modification is the next input, a drop-down menu again. Add a hole or open a door. The other choice is close a hole or open a door, which is probably not something you'd use very often, but I've used it. I mentioned it earlier. I once to do a test, closed attic vents up to find out my data. So now with the opening opened up, in this case the attic hatch, we use the house with reference to outdoor pressure. And again, this is baseline. I'm assuming we're using auto baseline or there is no baseline. The baseline 0, negative 50. And the house with reference to the zone, negative 15. And that corresponds with the previous slide that I'll go back to in just a moment. And then we have the blower door flow adjusted to 50 with the hole open, the modified zone, that's 2950. Go back to the illustration now. Here is the 2950, and here is the 15 that we used from the house to the zone. It's pretty simple once you go through a few examples to see how to use the tool. Now we are ready for the results. That's it. We've got approximately 6 entries, maybe as few as, well, 6 entries, primarily 6 entries, the rest are drop down. And now we have our results. So we're down here to the results section of the tool. The house to zone, the flow rate is 1400 CFM50 plus or minus 600. Now I'll mention more, that's the uncertainty. The 600 is the uncertainty. I'll mention a little bit more about that soon. The square inches, or this is the leakage area in square inches. You can choose the units. There's a drop-down menu for units. 140 square inches plus or minus 64. And the uncertainty is 44%. Now, you might think that's a big uncertainty, and this is really inaccurate. Well, zone pressure diagnostics has been inaccurate from the beginning, but you haven't always seen the uncertainty. The first tool that reported uncertainty was the ZPD utility on the Energy Conservatory website. We've reported it here. We think it's important that you know the uncertainty and you can learn by it. I could make these uncertainty percentages go down by doing some different things to the test. The zone to the outdoor. The zone is the attic. So 2000 CFM50 square inches is 210 plus or minus 72. That essentially is the effective square inches of attic venting, 210. And this is as good as measuring it, but this not only includes the vents in the gable ends or the soffit and ridge vents, it also includes other cracks. And then the through zone value, if we made either of these pressure boundaries perfect, this would reduce the whole house CFM50 by 1,000. So it's now 2,400. If we made either of these pressure boundaries perfect, for example, the attic floor, and stopped all leakage to the attic, we'd reduce the 2,400 by 1,000 down to 1,400. We do not give you the square inches of leakage for the through zone because it's not appropriate to divide that by 10. So that's that example. What do the numbers mean? Well, I've mentioned a lot of them. First of all, the house to zone of 1400. I've mentioned that already. Back to the tool. That's this one right here. And I think I will describe the slides coming up. And by the way, you'll be able to get the presentation from the Energy Conservatory website and from the RED website within a couple of weeks or so. So you can go back and review these numbers if you wish. These numbers mean that if we this is kind of silly and pretend, but if we totally remove the roof, the ceiling would leak at this rate, 1,400. Here, 2,000, which is zoned to the outdoor, if we totally remove the ceiling, the roof would leak at the upper part of the house would leak at this rate. The roof would leak at this rate. Now notice also that the through zone, or the total path, is a combination of the resistance to airflow of this pressure boundary and this pressure boundary. It's a combination. So the through zone leakage is always, always, always less than either of these by themselves. So just expect that, because both pressure boundaries, both air barriers, if you want to call them that, come into play with this value. But with this value, the roof pressure boundary doesn't come into play for this example. And with the 2000, the ceiling pressure boundary resistance doesn't come into play. So I explained these just now. And again, the total path or the through zone is the combination of the effect of the other two pressure boundaries. And it represents the maximum amount that you can reduce the whole house CFM50 if you make one of the two pressure boundaries perfect, which of course is unlikely. Oh, I want to go back and show you something on the tool. So I'm heading back there. Right at the bottom, I didn't mention this. I hope you can see it in blue font, so it means it's a result. The percent of the whole house leakage passing through the zone. This can be helpful. 42% of the whole house leakage of 2400 is leaking through the upper part of the house. 42%. That's pretty significant. Or, another way of putting it, 1,000 of the total whole house leakage of 2400 is leaking through the top of the house. The rest of it's leaking through the bottom part and the walls, windows, and doors. Now I'm going to advance again to where I left off. Okay. And this shows an illustration of the numbers that I just described. Here is the 2000, the flow through the roof and gable ends. Here, that is if the ceiling weren't there. Here's the 1400, the flow through the ceiling if the roof weren't there, and the total path or the through zone of 1000 CFM. So some of the facts about the RED tool, you don't have to measure the whole size. With the example that we just went through, there was no whole size measurement. That's an advantage. You may open or close more than one opening. That's not worded very well, excuse that. But let's say that you don't get the pressure drop, the pressure shift from your initial to your modified zone that you want. You can open another hole if another hole is available. Let's say if there happen to be two attic hatches, you open one all the way and you don't get the pressure shift you want, open the other one all the way also. And that will give you, it's very likely to give you more accurate results. So because you don't have to measure the hole size, you can open up what you want. You can use advanced inputs. I will show you this when we go to the live tool. We'll do that soon. It is very important when you use the RED tools that the RED tool that you enter the signs for the pressures. If you're doing bringing the house to negative 50 pascals, you must enter the negative sign when you put the values in the tools. I'll point that out in the next example. Notice the uncertainty values in the results table. I mentioned a little bit about that. I'll say a little bit more. Related to that, if you are going to use the RED tool, please do your best to try to read the user guide. I know many of us pride ourselves in not reading instructions, but the user guide can be very helpful when it comes to learning how to use the RED tool in particular and learning the restraints and limitations of zone pressure diagnostics in general. And again, on the live tool, I will show you you can click or touch on any input or result label for pop-up help. So if you wonder what a particular term means, or what do I enter here, just click or touch on the label on the tool, and a little help dialog will pop up almost instantly and give you instructions or describe things for you. So now another example, modified zone. This is an attached garage. Now Wisconsin comes to mind here. In Wisconsin, I know there are some people on this webinar from Wisconsin. Wisconsin requires zone pressure diagnostics being performed to the attic during the air sealing procedure. And I'll make you aware of their target in a short time. They also the auditors must, if there is an attached garage, do zone pressure diagnostic testing to the garage to see how leaky the common wall is between house and garage. So this example is an attached garage. So what we're going to do is put a hose out in the garage. We're depressurizing the house to 50 pascals. A hose goes to the garage. That is the zone now instead of the attic. Otherwise, things are the same. And so for our initial configuration, the door to the garage is closed. For a modified configuration, the door between the house and the garage is all the way open. Or you could open a door between the garage and the outdoors. Again, the size of the hole does not have to be measured. So let's assume the garage is the zone, and with the door from the house to the garage closed, we measure the whole house CFM 50 and we get 2250. Now we measure the house to zone pressure difference with our manometer, and let's say we get 32. Technically that's negative 32. And we measure the zone to the outdoor, delta P, and that's 18. These should add up to 50 or negative 50. Now we open the door to the garage. Usually that will be the pressure boundary that is the most resistant to airflow, so that's where we should open the hole or open the door. And again, we measure the house to zone CFM 50, and now we'll say that's 3,000. It stands to reason that that would go up. And we measure the pressure differences also. And in this case, we get a 0. So here's the tool. And notice here, I'm using with the initial zone, I'm using the auto baseline, so I've got 50 here, my actual pressure. And then I'm measuring from the house with reference to the zone and a negative 32. Notice for the negative 50, negative 32, the negative signs are entered. You will get an error message if it's not entered. And by the way, I haven't mentioned it, but this RED tool and others are pretty rigorous error catching capability. So if you put stop in here instead of 32, it will stop the calculation. Or if you put blue in there, or if you don't enter the negative sign, it will let you know. Because up here you've chosen depressurization, so it's going to be looking for negative signs here and down here. So make sure you put those in. So here we have the whole house CFM 50 with the garage door, the door between the house and the garage closed. The modified zone configuration, we have negative 50 created by the blower door. And when we open the garage door up totally, the pressure difference between the house and the garage is 0. That is quite likely to be the case when you do this, because the garage door, the swinging door, the passage door that you go through is a pretty darn big hole. So chances are now the garage will be essentially the same pressure as the house to the outdoors.
Rick?
Yes, Pete?
Rick? I had several people ask about the overhead garage door position, open or closed.
The overhead garage door position should be closed to create so that the outer boundaries of the garage create a pressure boundary or barrier. And if there is a door, a swinging door from the garage to the outdoors, which is often the case, that should be closed also. And I suggest if you do this test, if you modify the zone by opening a door from the garage to the outdoors, it will usually be just fine if you use the swinging door rather than an overhead door. With the swinging door open from the house to the garage, the whole house CFM 50 goes up to 3,000, indicated by the green arrow. Here we have the results. The house to the zone, for the initial zone configuration, we have 1,060 plus or minus 340 CFM 50. Again, the 340 is the uncertainty, and the leakage area, it's almost always this number over here, the 1060, not quite sometimes, divided by 10. So the leakage area between the house and the garage is 110 square inches, plus or minus 37 inches, for an uncertainty of 33%. The zone to the outdoor, this is something we usually don't care much about with an attached garage. This is the important number for an attached garage, the zone to the house. But here we have the zone to the outdoors, 1550 plus or minus 320, or 160 square inches plus or minus 37, and our uncertainty is 23%. And then the through zone, again, this is not a big deal for, not as big a deal for a garage, attached garage, as it is for an attic. 800 plus or minus 220. Now, in other words, what this means, this 800, if we were able to perfectly seal the common wall between the house and the garage, the whole house CFM 50 of 2250 up here would go down by 800 CFM 50. Pretty significant. So that's example 2. And the uncertainty, as I've mentioned, the Energy Conservatory tool, which you can get online, and I recommend you do that if you have a PC. The reporting of the uncertainty there with that tool is going to look, it's going to be less than with the RED tool, because with the values that RED is using, I'm going to go back and look at the uncertainty. These values are likely, the actual number of leakage is likely to be with 95% likely to be within this range of the 1060 plus or minus 340. Whereas with the Energy Conservatory uncertainty reporting, it's not as rigorous. So the numbers, the uncertainty values you get if you use that tool for the same example are only going to be half as much. That's something to keep in mind. Neither is wrong. They are both right. It's just that we decided to be a bit more rigorous with our numbers. I wanted to report to you just a little bit about some state weatherization standards before we go to the live tool. And there are 2 states I know of. I'm sorry if you're in a state that has some ZPD targets that you're using in your low-income weatherization program or other program, but these are the only 2 I know of, Wisconsin and Maine. and I happen to work quite a bit with each of these states. For leakage to the attic, the Wisconsin weatherization target, the through zone leakage to the attic should be, and this is a target, this is a should be, it's not a must, should be 10% of or less of the whole house leakage. The whole house leakage. So for example, here's an example. If the whole house leakage is 2200, the attic through zone leakage should be 220 CFM50 or less. 220 CFM50 or less. This is a pretty rigorous target. I respect it a great deal, and reports I have from Wisconsin folks is that they achieve this target much of the time they are air sealing an attic, and it puts a great deal of emphasis on making sure that that top part of the house is tight, and that's very important. So that's Wisconsin's, and this is one that's used in Maine, although it's not as stringent as the Wisconsin one. The house to zone CFM 50 of 30% or less in the attic square footage. So this is based on the attic square footage. So for example, if the attic square footage is 1,000 square feet, the house to zone CFM 50 should, and again this is a should, not a must, be 300 or less. 300 is 30% of 1,000 square feet. So that's the main target the state of Maine is using. And now for Wisconsin, this is a fairly new one for Wisconsin. The other ones have been around a while for the Wisconsin weatherization program. 50 CFM 50 target between the house and the garage. Again, this is pretty stringent. It is possible to achieve this. It takes a lot of good air sealing work to achieve it. So 50 CFM, 50 target. So if you divide 50 by 10 to get the approximate square inches of leakage, that is 5 square inches of leakage in that common wall between the house and the garage. That's really tight. Hooray, Wisconsin. In Maine, theirs is much higher. This could be lower by now in Maine, I'm not certain. They're using a target of 200 CFM 50 between the house and the garage. As far as I know, Maine was the first state to develop a target for this air leakage. And again, all of these are targets. They are not requirements, but they are targets for the weatherization crew to try to achieve. And what I'm going to do now it'll just take a few minutes. I'm going to go to the live RED tool. And this is what the web page looks like. Again, it's if you want to go there sometime, it's www.residentialenergydynamics.com. That is a mouthful. That's what it is. And that's what the page looks like where the zone pressure diagnostics tool is. The list of tools is over here, and there is some advertising there. So I'm going to shift now to So now I was just talking with my director-producer there for a moment. You should be able to see the live tool on your screen, and I hope it's a little bit bigger than the other ones were. It's the only thing on the screen. There's nothing else there. And a few things I want to show you here. First of all, the pop-up help. When I move my cursor and put it over one of the labels, you'll see that a question mark appears, and whether it's a result or whether it's an input, If I click on that with my mouse, or if I'm on a touch device like an iPad or a smartphone, if I click on that, a pop-up help appears, and it gives you instruction as to what this means. And you can get out of it by hitting the X in the upper right-hand corner, and that many things will do that. You can see, and you can have a number of these open at one time, and you can move them around. Okay, I'm getting the info that this needs to be bigger. I will do my best to make it bigger. Okay, I'm being told that I needed to make it bigger. And this is as big as I can go. I was full screen, so this, I hope you can see this now. Again, I'm getting a message that I needed to make it bigger. So it's now bigger, I hope. Okay, so again, if I do the pop-up help, you can see what happens. And it's fine with me. I'm glad you are reporting the things, that it's not big enough and whatever. That's very helpful. So you can see the tool better now than you were able to see before, although you can't see the whole thing, but that's okay. Now, this is already filled in, and this is filled in for the, I'll just scroll down, this is filled in for the garage example that we just did. I want to make that clear, and I want to show you another feature of this and all the RED tools. Here we have the results, and you can change the units. They're drop-down menus. You can change the units, square inches, square feet, and all the tools are metric ready. Maybe someday this country will convert to metric. And of course our Canadian friends they're already there, and they can change this to square centimeters or square meters. But I'll go back to square inches because most of us are familiar with that. And a few other things. There's a reset button up here, and the reset button takes you back to the default condition. And there's a print button. If you want a nice clean print without any advertising, without any other menus on the page, hit the print button. I'm not going to hit these now. And this blue circle with an eye inside is for information. That takes you to the user guide. So you've got the user guide you can read, and you've also got pop-up help that comes up instantly. Now I want to show you I said I'd show you advanced inputs. Again, this is the garage example that we went through. Again, I'll show you the results. We've got a house to zone of 1060, and our uncertainty is 33%. So try to keep that in mind. You'll notice that the tool, when I click here, the tool will automatically expand. And now I've got advanced inputs. What I can do here is adjust for temperature differences, as you can see. The default is 68, so it has no effect. You can change the pressure exponent, or some of you call it the flow exponent. You can change that. And also allowed ranges and normal ranges are given for most inputs. You can change that if you've done a multi-point blower door test. You can put that in here. Another feature is, if let's say you're doing something on a very windy day, you put in 3 baselines at 5-second intervals. That does not mean necessarily you set your digital manometer to 5-second averaging, but you take a baseline every 5 seconds, and let's say I have -3, 0, and -5. Well, what does that tell me? The average is -6.7. The variation in the 3 baselines tells me that it's windy. So if I come down here to my results, look at what it's done to the results. My uncertainty is going way up because of the wind. And my values have changed slightly. So the uncertainty reflects what's going on here. And if, on the other hand now, if I just want to take a look at that and see what happens with my results, that's fine. Now I unclick it, I deselect it, I go back, and I see that I have what I started with. So if you unclick something with this tool or others, it's whatever you enter in those input boxes does not have any effect on the final result. But if you engage it, if you click it, if you activate it, now it does have an impact on the final results. So moving down, now I can show you the drop-down menus because we've got a live tool. I'm showing this to you, by the way, with Safari, Safari browser. And these tools work on any computer device that has a browser. And you can see the negative signs. Yes. Yes.
Someone asked, using this tool with a smartphone, will the print button allow the document to be saved and or emailed?
Good question. No, the print button will not allow on a smartphone or on an iPad or tablet. It will not allow it to be saved. What you need to do is with whatever your device is, you need to determine how to take a screenshot of the tool. Try to get the entire tool on the screen, take a screenshot. I know with an iPad and an iPhone that's pretty easy. I assume it is with other smartphones and tablets. That screenshot is automatically sent to your photos, your photo album. And then that photo, as I think most people know that have smartphones and tablets, that can be emailed or texted or saved, printed back at your office if you have a Wi-Fi printer. So yes, you can save it, yes, you can print it, yes, you can email it and text it, but you have to do it in the proper fashion, and it's usually by taking a screenshot of it. That's a good question. So moving down again, the uncertainty is listed here, and we talked quite a bit about that. Now I think it's time to let's close things up now and take more questions. If there are any questions remaining there, I am not. Hang on just a moment here.
Rick?
Yes, Pete.
Was asked whether or not the tool could be used to actually measure attic venting, the actual size of or opening in either square inches or net-free area of an attic vent.
Yes, you can do that, and I can show you with the tool on the screen right now. If this, instead of this being a test to the garage, if we now assume this is a test to the attic, the house to the zone number shows us the square inches of leakage in this cell right here. The square inches of leakage between the house and the attic, and this value, the zone to the outdoors, tells us the square inches of leakage from the attic to the outdoors. So essentially 160 plus or minus 67. So that would be the effective attic venting, which would include the vents in place and cracks and holes that are also there and almost impossible to measure otherwise. So I think this is a fairly reliable figure. And think of this number in this way. We have 160. If we add 37 to that, that's 197 on that end. And if we subtract 37 from 160, that's the other end. So 160 is the center, is the middle of the range. So 160 is the number I would use if this were representing a test to the attic. That's what I would use for the attic venting, which I think is a pretty reliable figure. Pete, have you got another question?
Rick?
Yes, Pete.
Okay, let's see. Yeah, we've got a lot of questions. Some of them we're going to have to answer online. A question: why would you not want the attic the same temp and pressure with reference to the outside if you have a properly air-sealed ceiling plane?
Pete, I'm sorry, some of that was garbled. Could you repeat that, please?
Why would you not want the attic to be the same temp and pressure with reference to the outside if you have a properly sealed ceiling plane?
All right, I'm trying to understand the question. The questioner might be thinking about the only place temperature came up was with the use advanced inputs. And the reason that that's here, and you don't have to use this, the attic generally would be a different, we have zone pressure, the attic would be a different pressure than outside. And it would, of course, be a different pressure than the house temperature than the house temperature. But as temperature differs, as it goes up and down, the density of air changes. So this is an attempt by inputting temperatures here, if you wish to increase accuracy. It's essentially looking at the density of the air at that particular temperature, and it's throwing it into the calculations. If you do just a blower door test, for example, of a house, you'll get a different number if it's really cold outside than you will get if it's really warm outside. And that number can change by, say, for an open ring test, an open fan test, that could change by 10%. So that's what this is addressing, and I think that might be what the questioner might be thinking. This is the only place temperatures come up. And Pete, I want you to know, Pete, I cannot see the questions right now, so if you could just, okay, Pete, just hang on a second, okay? Okay, Pete.
Can you talk about why you can't use the CFM50 flow rate in combination with the pressure differences to get a leakage rate for a non-modifiable zone?
Yes, for a non-modifiable zone, meaning you cannot create a hole, because you cannot create a hole of any kind, you are not able to get the data that you need, obtain the data that you need to determine the flow rate. So unless you're able to open up a hole or close a hole, say an attic vent, to create a difference in CFM50 between the initial zone configuration and the modified zone configuration, you cannot determine the CFM50 flow rate. And if you cannot determine the CFM50 flow rate, you cannot determine the approximate square inches of leakage. So you're left with only the pressure differences and not the flow rates.
Sounds good. Let's take one more here. Why would you use advanced inputs if the uncertainty goes up?
That's a good question. The advanced inputs are there for such a case. For example, if it's windy outside, the advanced inputs, if you enter the 3 baselines that I did, that will give you the uncertainty that the wind brings into the calculations. If it's windy outside, it's difficult to get a static or steady or reliable blower door test reading, so that increases the uncertainty. It's not if it's windy, it's windy, and if it's really windy outside, it's probably a good idea to turn on the Use Advanced Inputs section of the tool, put in your baselines, and you might find that your number at the bottom, maybe this number is 1,000 plus or minus 1,200. and you might have an uncertainty percentage. It's possible to have an uncertainty percentage greater than 100%. You might want to say to yourself, if you have this option, it's just too windy to do a reliable test today, I'm going to come back. So some of you would not be able to do that. Say you're in North Dakota, you just drove 3 hours to do a weatherization job or an audit, and you're not going to come back. You'll do the best you can. But then you can quickly turn off, you can turn off advanced inputs. You can see what the uncertainty is without the wind, and then turn it on again and see how much the uncertainty the wind adds to the results, and that can be helpful to know.
Sounds good. Rick, let's take one more question here. This one comes up quite a bit. Question is, they're not sure where the building pressure exponent comes from or what it is. Can you discuss the exponents briefly?
The building pressure exponent, or the flow exponent as it's often described, by the way, in the advanced inputs it's right there, 0.65. If you deselect the advanced inputs, it assumes a flow exponent of 0.65, just as the Energy Conservatory DG700 does. This probably won't help much, but it's the slope of the house leakage curve, and that pressure exponent characterizes the type of leaks in the house. The range of the pressure exponent is between 0.5 and 1. That's the full range of it. And if all of the leaks in the house are characterized by long, skinny leaks, like through boarded wood siding, your pressure exponent moves toward 1. If your holes are characterized by primarily big round holes, not laminar ones, but round ones where there is a lot of turbulence as the air leaks through those, then the pressure exponent moves toward 0.5. But if you did, maybe in your area, did blower door tests, and by the way, if you do a multi-point blower door test, a test at a pressure of 10, 20, 30, 40, 50, 60 pascals, for example, that will give you the pressure exponent. But if you did 100 houses, you would probably find that the average pressure exponent was 0.65. And that's why we generally use that one as a default, and that's what is the default value inside of the computer chip in the Energy Conservatory DG700.
That's great, Rick. Thanks. Well, let's take. Let's try one more question here. When testing a non-modifiable zone, can we open a door to the house to obtain the data needed for the calculator?
For a non-modifiable zone, can we open the door to the house from the house to the outside? I assume to get the data we need. No, we can't. And if we're doing a test to an attached garage where we have a door from the house to the garage, that would then be considered a modifiable zone, not a non-modifiable zone. But no, for the question as stated, you cannot open a door to the house that is not attached to the zone in question to get the data needed to get the flow rate.
Great, thanks. Rick, I think thanks for hanging with us, going over and running this late. A lot of great questions. If you've got a question that has been answered, we'll be reviewing them and zipping them off and trying to answer for you. But thanks, Rick, for the great presentation today, and thanks to everyone that joined in. Bye now.
Thanks, everyone.